1240 to 340 lab for physics 110. The other thing I wanted to mention, and now that Yi Chen's here, this was something you brought up Thursday, and I forgot to mention it on Friday, about you worrying about the Gram-Schmidt orthonormalization procedure when you took the inner product in the opposite order or something like that. So here's a summary, of the Gram-Schmidt method, right? Remember, we say someone gives you a collection of vectors, V1, V2, V3, V4, an infinite collection of vectors, or they could be finite if you're on a finite dimensional vector space. The first one's easy, you just normalize it. That's going to be the first one in my orthonormalized collection. Then to get the second one, what I do is start with, to get the second unit vector, I first compute something that's not a unit vector. I take from the second one in my original list and subtract out its projection onto U1 hat, my new first element in the orthonormalized collection. And the projection, it has to be in this kind of manner here, okay? And then once I've got a vector that has no projection onto U1, then I can just normalize it and it will still have no projection onto U1. Okay, and similar for U3, I subtract out its projections onto U1 hat and U2 hat. Now, what Yi Chen, I think, was worried about, and it's a good thing to worry about because, it's not necessarily a trivial argument. Here's the argument I was making in class, which is the easy direction. If I take the vector U1 hat and multiply it, I didn't want to use U2 hat here just because it's complicated. It's divided by some junk that isn't really going to affect anything. But if I just take the inner product of U1 hat with U2, I'm hoping that's 0 because it's supposed to be an orthonormalized set, right? I'm not using the normalized version here, but it still should be 0. And my definition of U2, the non-normalized version of this, is this bunch of junk here. So I place that in parentheses and then I distribute this inner product. You look at your inner product axioms and you can distribute the inner product over parentheses and so on. And I get U1 inner product V2 minus U1 inner product V2 times U1 inner product U1, and this is automatic. We've already normalized it, and so therefore this is 1, and these two cancel out and give 0. That's good. That was the argument I was giving in class. Now, I think what Yi Chen was worried about is, well, wait a minute, what if we take the inner product in the other order? Well, we have to be careful about that because this function, when I put it on the left side of an inner product, which is what I'm doing down here, I'm doing this kind of thing. I have to take an inner product of a bunch of stuff with U1. And part of it is a constant that's sitting out in front of a vector. In other words, the thing I want to take the inner product with U1 has a constant sitting out in front of the vector, and that constant might be complex. Now, when I take the inner product, the function, anything that goes on the left side of the inner product has to have a star on it. And so if I have a constant that's sitting out in front, when I take the inner product and put it on the left-hand side of an inner product, it has to get a star on that because it might be complex, right? Then I distribute the inner product and I get this kind of stuff here. And I have a V2 inner product U1, and here I have a U1 inner product V2 star and a U1.U1, or this one's going to be 1 again. But the inner product gets a complex conjugate when you take it in the reverse order, and therefore these two things will exactly cancel out in the same way. It's just not as trivial of an argument. So that was just to clean up what Yi Chen asked about on Thursday. In any case, this is the Gram-Schmidt orthonormalization procedure where you successively subtract off projections onto all the unit vectors you've created so far. I think that's the only remaining things I wanted to talk about. So let's go back now into what we were talking about at the beginning of 3.2 after our big diversion into mathematics kind of stuff. We were talking about what operators are associated with dynamical variables. That means things that we can measure or properties that describe the state of motion of a particle, at least classically thinking, like position, momentum, total energy, potential energy. Those are going to be the big ones that we use a lot. Can any operator represent some dynamical variable? And the answer is no. In general, if you choose any old operator, you might get a complex number as corresponding to the outcome of a measurement. And we always need to get a real outcome. When we measure any property of a particle, position, momentum, total energy, and so on, we're not expecting complex numbers. It has to be inherently real. And so that motivates the following definition, which we gave at the end of last time. A Hermitian operator is one that in an inner product, and remember, Q, this vector, there's a lot hidden inside there, but let me just go to the board again. When we write this vector, Q, G, excuse me. Oh, I'm not focused, right, okay. Someone told me how to do that. Let's stop the video, start the video again. Hey, great, okay, awesome. Thanks for letting me know. Remember, this is just a symbol, just like, when I write a vector, I'm welcome to put any symbol I want there to help me remind myself of what it means. This symbol is universally used in quantum mechanics, and it's supposed to remind you that it's the vector that results when the operator Q hat acts on the vector G. So you just got to remember that that's what that notation means. So what is a Hermitian operator? It's one that when I have an inner product between two things, and the operator is on one side of the inner product, operating on the vector over there, it can be moved willy-nilly to the other side. And you have to prove that. This will work for some operators and it won't work for other operators, okay? And we're going to show very shortly that if you have a Hermitian operator, it's not clear that this is a good definition at all. Why would I care about this? Well, we're going to show in a theorem very shortly, and you've read it in Griffiths. And in fact, you're going to be responsible for knowing the proof of the theorem because it's so simple. That when you take this definition, the expectation values and the measured values of corresponding to this operator will all be real. And therefore, when you measure the physical quantity corresponding to this operator, you're always going to get a real outcome. Okay, now, we said that for most operators, it's not true that when you move the operator over to the other side of the inner product, and we'll talk about how to do that in just a second. I'll remind you what we did on Friday at the very end. Usually when you put the operator over there, it changes. And we're going to call that changed operator O dagger. Okay, it's got that little kind of cross symbol as a superscript. And that's called the Hermitian conjugate or the adjoint operator. Different people use different terminology for it. Okay, so in general, when you have any old operator and it's sitting in an inner product, so here's a state F with O operating on G, we're going to think of that, it seems a little bit abstract to write it this way, but at least if we're representing these states as functions of X, which is the good old-fashioned way we're used to doing things, right? We would say, oh, it's an inner product. That means the integrate from X equals minus infinity to infinity, put an F star of X over here, and then put your operator operating on G of X and integrate, right? And when I say this operator here, I mean the appropriate operator, whether it be a differential operator or whatever, that is ready to operate on a function of X. Okay, so for the momentum operator, this would be a minus I h bar d dx. For the operator, this would just be an X there, right? And the question is, how can I get it moved onto the F over here? In other words, can I do some manipulations so that this turns into some other operator, which we're going to call O dagger, operating on f of x. That's all under that complex conjugate there, times g of x dx. Whatever that operator ends up having to be, we're just going to call that the Hermitian conjugate of that operator. Okay, so we did some examples, and what I want you to do is some other examples. So let me pass out a worksheet. This is the worksheet for you guys at home that is listed under Friday's date, I'm pretty sure. So look on our course website under Friday and you'll find a worksheet. At the top it says spectrum. And you know, there are 4 operators there, and I'm asking you to find the Hermitian conjugate of all of them. Well, you'll get better at this with intuition, but let's try. What I want you to do is 2 of them. Maybe the last 2 in the list of 4. That is Ix and ddx. So you're supposed to find for those operators what their Hermitian conjugate operator is. And if the Hermitian conjugate operator is the same as the original operator, we would say it's a Hermitian operator. And we're not doing problem 2 now. We'll do that after a couple more definitions. Okay, if you're unsure where to start, we're going to start with the inner product where we have an f of x with a star happening to it. And then we're going to put our operator, maybe ix, operating on g of x, and then integrating from x equals minus infinity to infinity. And somehow I want to take this operator, in this case, it's just being multiplied. So I can kind of move it around, but I have to worry about that star. What happens when I take an ix and move it under that complex conjugate symbol? What happens to the I? What happens to the x? Okay, just to make sure everybody's on the same page, let's continue on with this example. So I want to get this ix. It's not a differential operator, so I don't have to worry about moving it around under here. I can certainly move it over next to the f of x star, ix, f of x, which has a complex conjugate on it, g of x dx. Now I want to get it under the star. So isn't it true that I is the same thing as minus I star? Right? If I take the complex conjugate of minus I, I just get I, which is what I had before, right? And well, I can put a star on an x because as we discussed on Friday, x is always a real variable for us here. In other words, we may have complex valued functions of x, but x itself is always real, right? We're talking about a number on the real axis. So x is the same thing as x star. And if you have the complex conjugates of a bunch of things, you could write that as minus I x f of x, all under the star. So this, what I've got written over here, I would write, just in the abstract notation, this might be f O operating on G for our O operator being Ix. This one would represent some operator, which we're going to call O dagger, operating on F, inner product with G. And that operator O dagger, I can see, because the star goes on everything on this side, this, my operator O dagger, is multiplication by minus Ix. Okay, technically, because it's going to change in different bases or different representations, this is what the operator looks like when it's operating on functions of x, but it'll have, as we discussed when we were talking about matrix elements, when you change bases or representations or which way your axes are oriented, those operators can change. But for right now, we're just thinking of it as something that multiplies a function of x. So our operator O was Ix, our operator O dagger is minus Ix. That means it's not Hermitian. If these two were the same, we would call it a Hermitian operator, but it's not Hermitian. What happens, well, I think we already did this other one, ddx. What happens in the case where I put a ddx here? What was the argument? How am I going to get a ddx to move over there? I can't just willy-nilly move a derivative through off of one thing and onto another. So what do we do to get it onto the other side? Integration by parts, right? We all at least have some kind of memory of saying, if I have a function times the derivative of another function under an integral, that's equal to a boundary term, which is just get rid of the derivative, f of x star g of x, evaluated between the two limits. At least in physics, we call that a boundary term, minus the integral with this derivative placed on the other one. Okay, so integral minus infinity to infinity of the derivative with respect to x of f of x star. I better put parentheses around this because this derivative is no longer operating on the stuff that's over here, g of x dx. Now, in my solution, now you have to make a little argument here that I can write this as the derivative with respect to x of f of x all underneath the complex conjugate. And maybe that's a little bit confusing, but I have an argument in my solution where I say, let the function, let this function be an arbitrary function with real and imaginary parts, right? And I'll let you look at the solution. It's probably not worth explaining now, but the fact that you can put the derivative underneath the star and you get the same thing out. Certainly for real functions, that's not going to be consequential, but for complex functions, at least sounds a little bit confusing. Now, what's the argument about the boundary term? What did we say about that? The whole context is we're talking about the vector space, capital L2, minus infinity to infinity. And so the claim is, for these functions to be normalizable, they have to head to 0 as you go out to plus infinity or out to minus infinity. And therefore, the product of them is certainly going to head to 0 as you go to plus infinity or minus infinity. And the boundary term goes to 0. Now, I can put the derivative under the star. I can also put this minus sign under the star. So I can think of this as being the integral from minus infinity to infinity of minus d dx f of x, all under the star, g of x dx. And that's telling me if my original operator is d dx, my Hermitian conjugate operator is minus d dx. And therefore, again, this is not a Hermitian operator because O is not equal to O dagger. Hermitian operators are called self-adjoint operators because they're equal to their own adjoint or Hermitian conjugate. Now you can imagine how to cook up a Hermitian operator out of this, right? I got an extra minus sign, but notice if you put an I in front of something, you get an extra minus sign when it goes under the star. So I could sort of fix this up by putting an I out in front of it. And indeed, you can check, you can probably do it in your head, that this is going to be a Hermitian operator, which also means that minus I h bar d dx is going to be a Hermitian operator, and it better be because it is the momentum operator. And the claim is we want Hermitian operators to be our physically measurable dynamical quantities. You've seen all the hardest case. I mean, really, any other operator that you form, you're going to have to, it's either some derivative operator or some functions of x or combinations of the two. Functions of x, you can just move around. Derivative operators, if you had a second derivative operator, you would have to integrate by parts twice. So let me just to test your intuition. What about this operator? It's not on the worksheet. What do you think would happen if I said, what's the adjoint of the operator second derivative with respect to x going to be? Will it be equal to its own adjoint or not? Why, yes. Just in a sentence, what's going on? Right. I mean, you have to think about the boundary terms, but if you think, okay, I make an argument about the boundary terms for each one of those steps, and let's imagine that each time you end up with an overall minus sign. When you put one derivative over on the other side, you get a minus sign. And then when you move the other derivative over to the other side, you get a minus sign. So when it's totally off the G and onto the F, I've gotten two factors of minus signs, which gets me back to a plus sign. And so this is a Hermitian operator, which means, for example, the kinetic energy operator, we might call that K hat. Certainly that's a dynamical variable, and it should correspond to a Hermitian operator, and that has the formula P squared over 2m. P squared is going to be, when I take P squared, I'll get minus h bar squared over 2m times d squared dx squared. So if this is Hermitian, hey, I've just multiplied by a real number out in front of it. This combination is still going to be Hermitian. As long as I don't have any i's out here, it doesn't affect the hermeticity of that operator, as people would say. Okay, I'm sure there's some questions in the homework about showing whether some operators are Hermitian or not, but you can practice more with those in the homework. Any questions on that stuff? I'll let you think about this, and then you can look at my solution to the worksheet. I've got a little side note down at the bottom of why the derivative goes under there. And maybe you think it's either really obvious or kind of obscure. All right. Some more important stuff about Hermitian operators. Determinate states. If we have a Hermitian operator, are there any states where if we measure, so we're claiming that Hermitian operators correspond to measurable quantities or dynamical variables that we might measure. And so we could say, if we measure that quantity, is it ever possible that we could put a particle in a state such that we would only get one possible outcome? In other words, we don't get some rho as a function of Q for that operator, but we essentially get a delta function. Only one non-zero value is going to be measured. So that would be sort of like for our energy operator, the Hamiltonian, we found those states, right? We said, if you're talking about the harmonic oscillator potential, and we wrote down the exact formula for the function psi3, and we showed that if you're in the state E equals, I guess it's 2 plus 3 plus 1/2 h bar omega, you're going to have there's a definite energy. And if you try to measure the energy, you're not going to get any other outcomes for the energy. So for any given operator, can we find states such that if the particle is in that state, the uncertainty or standard deviation associated with that probability density function is 0. In other words, there's 0 probability of measuring a different value. And the answer is yes. So if you look at the notes, there's a little quick argument here, but I'm not going to go through it on the board just to try to not put too much details in here. But the upshot is, after a couple of arguments and using the fact that this operator is Hermitian, you get down to this state that if there's going to be a definite Q state, then it has to be true that the operator Q minus the eigenvalue, minus a particular value of Q operating on this state psi Q. So we're presuming here that we want this state to be a definite Q hat state that's centered on value little q. This has to be true. And then we go back to our we don't have to go back to anything. I'm thinking of a different argument here. All I have to do is distribute this out and put q times this on one side and little q times that on the other side, and we find that we've gotten down to an eigenvalue equation for q. So the upshot is here that if you want a state where when I measure the operator q, I only get one value, little q, if I measure the dynamical variable associated with that operator and can only get one q value, which in this example I'm calling lowercase q, then this has to be true of that state. Q operating on that state, which we're going to call psi q, is equal to little q, which is to say that this is an eigenvector of this operator, and this is the corresponding eigenvalue. So to put it in different words, if you want to find definite states for a certain operator, ones for which there's only one possible measurement value for that dynamical variable, you should find the eigenvectors and the corresponding eigenvalues of that particular operator. And usually that amounts to writing down a differential equation and solving the differential equation. We've done that already for the total energy operator for certain potentials, right? But it's true for other operators too. We could find the states of definite momentum. We could find the states of definite kinetic energy and whatnot. Okay, here's another definition. The collection of all possible eigenvalues of a particular physical operator or an operator corresponding to a dynamical variable or a Hermitian operator is called the spectrum of that operator. So we already used this in the context of energy. We said the energy spectrum of the total Hamiltonian operator, the total energy operator, is the set of allowed energies of it. And I believe I used it in this more general context. If you solve for the eigenvalues of an arbitrary operator, the collection of all eigenvalues is called the spectrum of that operator. And the corresponding states that correspond to those eigenvalues are the corresponding eigenvectors. Or if you're thinking of them as functions of x, they're called eigenfunctions. Now, it's worthwhile going back to what we know from chapter 2 and thinking about the cases here, because to be considered an eigenvalue of an operator, you have to be associated with an eigenvector that lies in the Hilbert space that we're talking about. And most of the time, the Hilbert space we're talking about is capital L2 on the full real number line, square integrable functions. So, for example, we said, in so many words, we found back in chapter 2 the eigenfunctions and eigenvalues of the Hamiltonian operator, right? We wrote it like this: h psi of x is equal to e times psi of x. And in fact, that eigenvalue equation we call the time-independent Schrodinger equation, but it's an eigenvalue equation for a particular operator, the total energy operator. And if there are lots of different Hamiltonians. It depends on what potential we use. If we choose our potential energy to be 0 everywhere, that corresponds to the free particle. Then, if we're talking about the free particle, what size and what ease did we get? Can you guys tell me what we found? What were the solutions to the time-independent Schrodinger equation? Yeah, for the free particle. E to the I kx, right? We made an argument that you could choose a preferred normalization, but a normalization times e to the I kx, so we might call that psi k, right? And essentially all of these between, minus infinity and infinity, I might write it this way. K is between minus infinity and infinity. That's an infinite collection, continuous collection of functions. Now, are these functions, these eigenfunctions or eigenvectors, if we're thinking of the functions as vectors, do they lie in our space of square integrable functions? No, they don't. And so we would, corresponding to these, we would say, well, I could index them also by E. The relationship between E and K is E is equal to h bar squared, K squared over 2m. That's just P squared over 2m because the total energy is equal to the kinetic energy for the free particle. So none of these lie in the vector space of square integrable functions. And so, at least on the surface of it, we would say, well, look, none of these is an eigenvector. And none of these corresponding E values is a corresponding eigenvalue. And so if you wanted to be a real purist about it, you might say, well, the spectrum of the total energy operator for the free particle is empty. There is no spectrum. Right? The spectrum is the collection of all eigenvalues. But we would say there aren't any eigenvalues because every eigenvalue's got to correspond to an eigenvector, and there are no eigenvectors in this case. Okay, so if our Hilbert space is capital L2, the corresponding eigenfunction has to lie in capital L2. Okay, so in some cases, we're going to have to think a little bit more, and we're going to follow Griffith's lead here in trying to expand our Hilbert space a little bit bigger than capital L2 to accommodate these, even though we won't technically call them eigenvectors. We want to still include those corresponding energy values in the spectrum. Okay, here's another definition. There's just a bunch of definitions, and we're going to play around with these more and more. If two or more linearly independent eigenvectors share the same eigenvalue, we say the spectrum is degenerate. That's kind of like, do you remember if I take one of these two, I know I just made an argument that we shouldn't really consider this to be an eigenvector, but if I take a particular k, say k0, a e to the I k0x, and here's another linearly independent function, a e to the minus I k0x. These are linearly independent of each other. One is not a multiple of the other, for sure. Now, in this case, they correspond to the exact same energy, because notice the energy just depends on the square of the k value, and you can think of, here's one positive and this one comes with minus sign, and therefore the energies are exactly the same in this case. So if I were to consider these two different eigenvectors, they would correspond to the same energy eigenvalue. So we would say, just to reference this definition, that the Hamiltonian in this case has a degenerate spectrum. Degenerate just means more than one eigenvalue, more than one eigenvector corresponding to an eigenvalue, linearly independent eigenvector. Okay, let's look at, just to play around with these definitions. This is supposed to be really easy and just write it down. You just have to think about what the definitions mean. 2, consider the total energy operator, Hamiltonian, for the harmonic oscillator potential. Write down the spectrum of this operator and characterize it by answering the following questions. Is it real, the spectrum, or inherently complex? Is it degenerate or non-degenerate? What about how many elements are in it? Is it a finite collection of eigenvalues, discretely infinite, or a continuous collection? So just think about those. I mean, it shouldn't take long to think about them but follow the definitions that are given up here. Okay, help me out by first helping me write down the collection of all eigenvalues of the total energy operator. I'm just using different words for something that we've already solved before. All eigenvalues of the total energy operator corresponding to the harmonic oscillator potential. That's right, I could write them this way. N plus 1/2 h bar omega. Those were our allowed energies. For n equals 0, 1, 2, and so on. Any non-negative integer, right? So that's the spectrum. Of the Hamiltonian operator. Is the spectrum real or complex in this case? It's definitely real. It better be real. I mean, of course, they're measurable quantities. That's the whole point. So this better correspond to a Hermitian operator. Is it, what else did I write? Degenerate or non-degenerate? It's non-degenerate. That means for each one of these energies, there was only one psi, right? We had psi 0, psi 1, and psi 2, and so on. Each one of these is a polynomial. This was a polynomial of degree 1, the Hermite polynomial, times a Gaussian function. This is a polynomial of degree 2 times a Gaussian function. And there's no two of them, unlike what happened with the free particle, where we had two different K values that corresponded to the same energy. And so there was a degeneracy there, two different states. And in this case, it would be discretely infinite, right? There's an infinite collection of numbers in here, but not a continuum, not a finite number. Okay, just an example there. Any questions on that? Okay. I didn't check your reading responses today, but again, just to implore you, I do read the reading responses, and I know it's been a while since I got ahead on the reading, and we are getting back to, we'll get into 3.3 soon, but try to add to those reading responses. I like referring to them in class, and so if you haven't been doing that, try to add those in, and I'll make reference to some of them in class. Okay, so we just found out about determinate states. Yes, we got those. Okay, I think that was a review from a different semester. So, and this is exactly the, okay, so here's an example that corresponds very closely to what I was just saying, right? Let's find the energy eigenvectors. They have to lie in capital L2 for the free particle, right? So we solve H psi equals E psi. That's the same time-independent Schrodinger equation that we found before. And we thought through it. It's pretty easy to solve. We have oscillating solutions of both directions. We could write it as cosines and sines, or I've written it as complex exponentials here. Whenever you do that, you've just solved a differential equation. You should always provisionally label those as potential eigenvectors. Okay, and the energies are all positive energies, right? Whether or not you have a negative K or a positive K up there, the energies are all non-negative numbers. It's potential because you have to always check, I've solved for a function, but does this function lie in the original vector space? And the answer is, in this case, no. So it seems like there's a problem. If you really want, if Griffiths would say, if you want to be a purist about this, there are no eigenfunctions and eigenvalues of the free particle energy operator that lie in our vector space, our sort of default vector space of square integrable functions. So that's doesn't sound very interesting. Nonetheless, we found that those functions were really useful, right? We found out that we could write a given perfectly square integrable function as a linear combination of those non-normalizable functions, and the coefficients were given by the Fourier transform. So what we're going to do is expand our notion of the vector space a little bit. We're not going to make the vector space bigger, but we're going to add some things sort of on the outside of the vector space in the following. You have to kind of read, I think this is in some of the footnotes in Griffiths. We can expand capital L2 to include some non-square integrable functions. We're not going to allow functions, and we'll talk about why in just a second, or how we eliminate them. But we're going to allow functions that oscillate as they go off to plus and minus infinity, like e to the ikx. The dividing line is going to be that they still have to have a finite inner product with functions that are actually in capital L2. Why? Because we found out earlier that if I want to write, let's imagine that this is a perfectly square integrable function at time t equals 0, right? And I want to write it as a linear combination with some coefficients. We called those phi of k times e to the I kx dk, if I want to write it that way. Then the formula for phi of k was 1 over root 2 pi times the integral from x equals minus infinity to infinity of psi of x0 e to the minus I kx dx. And notice what this is. This is an inner product. I might write, sort of in symbolic notation. This is kind of like taking the abstract vector that corresponds to the state e to the I kx and taking its inner product with the state that might be labeled as psi at x at time t equals 0. That's kind of a crazy notation, but it's we want to take the inner product between this and this. And whatever vector gets on this side, it needs to be complex conjugated inside there. So this is kind of an inner product that we're doing there. And that's okay, because as long as this is a square integrable function, its inner product with this is going to be perfectly finite, and this whole kind of technique makes sense. If this function were so poorly behaved, like it was e to the x or x squared, something that just keeps going up bigger and bigger and bigger, not just oscillating as it goes to infinity, but keeps blowing up, then it wouldn't have a finite inner product with an arbitrary square integrable function. And so we're not going to include those kinds of functions in this space. We really don't need them because we couldn't find the coefficients associated with them anyways. The integrals would diverge. Okay, Griffiths follows somebody else's book, Ballantine, and calls this a rigged Hilbert space. So rigged Hilbert space means we have a vector space and we're just going to add some extra functions on the outside of it. And we're going to use those functions as part of our basis sometimes. And we'll be able to write things as a linear combination of them, but they don't have full-fledged membership in the vector space. In other words, they're not in the capital L2 part. Some subset of this vector space is going to be, but it also includes some functions like e to the I kx, which aren't quite in there. But if I took the inner product with e to the I kx with a square integrable function, it would still be perfectly finite. I know this is a little bit overwhelming, but a lot of this stuff, we sort of build up the definitions and then practice with them. So here's what we're going to do. We're going to take our original Hilbert space, capital L2, and we're going to add the following kinds of functions, those that are not square integrable, but still have a finite inner product with functions in, this should say L2 with the 2 as a superscript. That's just a typo on my part. And delta functions too. Delta functions technically weren't in our original, they're not functions per se. Functions can't have infinite values and be infinitely squashed together. But just checking the time there. Okay, so that means that some of the things that we've defined on our Hilbert space are only going to be defined for some of the elements of the rigged Hilbert space. We can't calculate the norm of e to the I kx. Its norm is formally divergent, so we wouldn't say that it has a norm. The norm is defined on all the functions in the rigged Hilbert space that are purely square integrable. The inner product is defined only if one of the vectors is in the capital L2 part. The other one can be in the auxiliary part. And there's a more general definition of what Hermitian means. Again, you won't see the importance of this here, but when you do, in the definition of Hermitian, one of these functions has to be in the L2 part, and one function can be in the extended part of the rigged Hilbert space. And so that's extending the definition of Hermitian. So the idea is we don't want to say that there are no energy eigenfunctions and eigenvalues for the free particle. So if we say now instead of operating in capital L2, we're operating in the rigged capital L2, we can now say that the spectrum includes all these energies from 0 to infinity. And the collection of eigenfunctions or vectors includes those e to the ikx kinds of functions, okay? So just to summarize, on L2 rigged, the free particle energy eigenfunctions, again, you can choose that preferred normalization, but the important part is the e to the ikx. The spectrum is, in this case, the spectrum is real, right? It's not inherently complex. The spectrum is, the energy spectrum is continuous in this case, and degenerate or non-degenerate? It's degenerate, and that's because we have two linearly independent states, e to the ikx and e to the minus ikx. And both of those correspond to the energy eigenvalue, E equals h bar squared k squared over 2m. One energy eigenvalue and two linearly independent states. So it's degenerate. So you can see we're working really hard to pull together a lot of things we found out in chapter 2. I think this is just kind of a repeat of what was said there, okay? And generally, if we have these other states that aren't in capital L2, but they're in the rigged, the extended part of it, they generally form a continuum rather than a discrete set of vectors, and we can Dirac orthonormalize them in the sense that is hard for us to do. It takes a lot of work, so we're not going to worry about it, but we're just going to think in the back of our head that someone is going to Dirac orthonormalize them for us. We did it for the free particle energy eigenfunctions. The other cases we're just never going to worry about. All right, where are we time-wise? I'm going to write down a theorem that we don't have time to prove, and it's an important theorem. So on Wednesday, we're going to go through it carefully, and I want you to be able to state it, actually prove the theorem. The theorem has two parts. If we have a Hermitian operator, so this is essentially a statement of two different theorems. If we have a Hermitian operator and it has a discrete spectrum, so we could be talking about Hamiltonian with a discrete collection of energies, or some other operator that we've made up that has a discrete spectrum. It's got to be Hamiltonian. Then its eigenvalues are all real, and that's important to us because we found out that the eigenvalues of the operator are going to be the measurable, the outcomes of measuring this dynamical variable. Has only real eigenvalues, and the eigenvectors corresponding to distinct eigenvalues are orthogonal. That was something that just seemed like coincidence back in chapter 2, that, for example, psi2 is orthogonal to psi1, and psi2 is orthogonal to psi3. That was a case for the Hamiltonian operator. The same is going to be true for any other operator that has a discrete spectrum. And we'll actually prove a different, or at least won't really prove it, but we will sort of argue as best we can through a continuous spectrum, an analog to this. Things get a lot more difficult with the continuous spectrum. But both of these consequences are pretty easy to follow, the proof of it. So we'll do those on Wednesday. So we're now just getting into section 3.3. So you still have no reading for Wednesday. Work on that homework. I will look and see what I think we're still not